In the last section, we learned about margins of error and confidence intervals for the mean, and that was assuming that you knew the population standard deviation. We're now going to look at how to establish those confidence intervals when the standard deviation for the population is not known. As long as your random sample is at least of size 30, or is taken from a normally distributed population, you can use the sample standard deviation to estimate the population standard deviation. So we would use the sample standard deviation as our point estimate. However, when you use that sample standard deviation, the sampling distribution of the mean does not follow a normal distribution. So where in the past we could calculate z-scores and use standard normal table, we can't do that anymore. However, it follows something known as a t-distribution. A t-distribution is very similar to a normal distribution with some minor differences. So if the distribution of a random variable x is approximately normal, then t, which is defined to be the sample mean minus the population mean divided by sample standard deviation divided by square root of sample size, will follow a t-distribution. And just like with z-scores, we labeled the critical z-scores z sub c. Critical values of t are denoted by t sub c. Here are the properties of t-distributions. So the mean, median, and mode will all be equal to 0. The t-distribution will be bell-shaped and symmetric about the mean, and the total area under the curve is equal to 1, just like it was for a normal distribution. The key difference here is the tails, or the low parts of the graph, are thicker than those in the standard normal distribution. The standard deviation of the t-distribution varies with the sample size, but it is always greater than 1. And because it varies with the sample size, we have this new characteristic that we call degrees of freedom. The t-distribution is really a family of curves, and that sample size is controlling what the curve will look like. Degrees of freedom, which we abbreviate D period F period, are the number of free choices left after a sample statistic, such as the sample mean, is calculated. So when you use the t-distribution to estimate a population mean, the degrees of freedom are always equal to 1 less than the sample size. And in your book, they give the example of students arriving in class. If there's 25 people in class and 25 chairs, the first 24 people who walk through the door are going to have choice in terms of where they decide to sit. However, once you get down to that 25th student, there'll only be one seat open. That person no longer has a choice. That's the same idea here, that the degrees of freedom will be 1 less than the sample size. As the degrees of freedom increase, the t-distribution becomes closer and closer to the standard normal. Generally speaking, larger sample sizes are better and will, again, more closely approximate just a standard normal distribution. The first thing that we're asked to do here is to find the critical value T sub c for a 95% confidence level when the sample size is 15. So in this particular example, our C value, our confidence level that we're looking to establish, is 0.95, 95%, and our sample size is 15. So remember, degrees of freedom are always sample size take away 1, and 15 take away 1 is 14. So in order to determine the critical value for this t-distribution, you need to use Table 5. Table 5 is provided in the very back of your textbook. I will post it as a PDF as well. And you'll notice the first column is labeled degrees of freedom, and then you have levels of confidence going across the tops of the columns. And so in this particular example that we're working on, we just said the degrees of freedom are 14. So you go down to the number 14, read across, and we wanted a 95% confidence level, which takes me here to the number 2145. So my T of C value, which is what I was asked to find, is approximately 2.145. And that's all this example wanted you to do, was to find that. Now, once you know that critical value, the steps are going to be similar to the ones you saw in the last section. So hopefully you understood that pretty well, because this is going to be similar with some minor differences. And then there is a note here. When you're using this table, you'll notice as it gets down to the bottom, it starts to skip over some numbers. It goes from 39 to 40, then 45, 50, 60, 70, 80. If the number of degrees of freedom you need is not in the table, you are supposed to use the closest number in the table that is less than the value that you need. So, in other words, if you were trying to look up degrees of freedom and it was 54, let's say, the closest number in the table that is less than 54 would be 50. So, in that instance, I would use 50 degrees of freedom. This will result in having a slightly larger confidence interval with a slightly higher level of confidence, but provides a reliable estimate. To calculate the margin of error when the population standard deviation is not known, the formula for E is, and so again, this formula is going to look similar to the formula in the last section, but instead of Z sub C, we now have T sub C. And in the top here, we have the sample standard deviation divided by square root of the sample size. Now, the sample, again, has to be random, and either the population is normally distributed or your sample size is at least 30. So let's try getting the margin of error in example 2. We randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 162.0 degrees Fahrenheit with a sample standard deviation of 10.0 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. So again, we're trying to take the results of a sample that we have and then generalize about the population mean. Now, we are told we can assume the temperatures are approximately normally distributed. And again, that's important here because we can't use our margin of error formula to help us get the confidence interval unless we know that. So now I'm going to jot down what I've been told. There are 16 coffee shops, so that's my sample size. The sample mean temperature, X bar, is 162 degrees, and the sample standard deviation, little s, is 10. So again, this is a situation where we don't know the population standard deviation. We want a 95% confidence interval, so that is my C value written as a decimal. And we want to write a confidence interval, but the first step in getting a confidence interval is always to find the margin of error. So before I'm ready to go to this formula, I will need my T sub C value. So I need to take my sample size and calculate what my degrees of freedom will be by subtracting 1. And with that piece of information and my confidence interval, I'm ready to go look at table 5 and find my T of C value. If you go ahead and do that, T of C turns out to be 2.131. All right, now I can go to my formula. I will substitute the values in the appropriate spots. So 2.131 times 10 divided by the square root of 16. All right, if you calculate this value, it will be approximately 5.33. I'm taking two decimal places here because our measurements have a single decimal place on them. And once you know that, you're going to use the same formula you're familiar with to establish the confidence interval. Namely, the sample mean minus the error will be less than the population mean, which is less than the sample mean plus the margin of error. So we were told the sample mean is 162. So I'm going to have to take 162 minus 5.33 will be less than my population mean, which is less than 162 plus 5.33. And that gives me boundaries of 156.67 degrees Fahrenheit and 167.33 degrees Fahrenheit. If you're asked to interpret, you would say we are 95% confident that the population average temperature of coffee sold will be between 156.67 degrees Fahrenheit and 167.33 degrees Fahrenheit. Here's another example. Again, these really aren't too difficult if you understood the last section, but we'll do another one. You randomly select 36 cars, so there's our sample size, that are the same model sold at a car dealership, and determine the number of days each car sat on the lot before it was sold. The sample mean is 9.75 days, with a sample standard deviation of 2.39 days. We're told we should try to construct a 99% confidence interval for the population mean number of days that the car sits on the lot. So you can see I've written my variables as I was reading through the problem. And the only other additional piece of information I'm going to need is my T of C, which comes from knowing my degrees of freedom. I actually skipped a step here. Please notice our sample size is at least as big as 30, so therefore I can use the T distribution in this case. My degrees of freedom is one less, so it's 35. And so I'm now going to go to table 5, look up 35 degrees of freedom and a 0.99 confidence level, and my critical value is 2.724. Now I can use the margin of error formula, put the numbers in the appropriate spots, and I'm going to give my answer to 3 decimal places here because my days are being measured to 2 decimal places. So this value is approximately 1.085. Now we use the confidence interval formula for the population mean, substitute, and calculate. And here are my results. If I were asked to interpret this result, I would say we can be 99% confident that the population mean number of days that this car model will sit on the dealer's lot will be between 8.665 days and 10.835 days. So the last thing we need to do is really summarize the last 2 sections because they work hand in hand. So this flow chart appears in your textbook, and I've just replicated it here. And if you are trying to decide whether you should use the standard normal distribution or the T distribution to make your confidence interval for a population mean, you start here and determine if your population is normally distributed or the sample size is at least 30. If the answer is no, you can't use either one of these distributions. So assuming the answer is instead yes, then the deciding factor is, do you know the population standard deviation? If you say yes, then you're using the standard normal distribution. You'll need a critical value, Z sub C, and you'll use the standard normal table. If you don't know the population standard deviation, you're going to approximate it with the sample standard deviation, and you will use a t distribution, which requires a critical t value. And that, again, you will get from table 5. So hopefully that helps clarify the difference. And the last example is an example where you have to go through that whole process. You randomly select 25 newly constructed houses. The sample mean construction cost is 181,000, and the population standard deviation, that word's very important there, is 28,000. My sample size again was n. Assuming the construction costs are normally distributed. So that's that very first question in the flow chart, is whether or not your sample is normally distributed or whether it's at least 30. Should we use the standard normal distribution, the t distribution, or neither to construct a 95% confidence interval for the population mean construction cost? The deciding factor is right here. Because this is the population standard deviation, we are heading towards using the formula E equals Z sub C population standard deviation divided by square root of sample size. If we did not know this piece of information, hopefully instead we'd have the sample standard deviation, and in that instance we would use the t distribution version of that formula. So all this question wanted us to do is to determine which of these options we would use. So the answer here is, if we're using a critical z-score, that's the standard normal distribution. And that is because the population standard deviation is known. And so if you were to actually try to determine the confidence interval, remember the next thing you would do is, if this is my C value, you would go to the table, look up the critical z-score that you need, and then head off to your margin of error formula.